Okay, so switching gears away from van der Waals, now we're going to talk about something called an ion pair or a salt bridge. Ion pair and salt bridge are interchangeable terms. They mean the same thing. I will use them interchangeably. They are not an ionic bond, okay? We talked about an ionic bond earlier. We talked about this as actual electron transfer between two ions. They're interacting. This is not. We're talking about an interaction between two atoms or groups of atoms that bear a charge, but we're not talking about electron transfer. Okay? And an example would be two amino acids that are near each other folded up in a protein. So here we have glutamate and arginine. Once the protein is all folded up, and again, protein structure is going to be next week's conversation, primarily on Monday. But if these two charges come in close proximity to each other, they can participate in an ion pair or a salt bridge. Okay? So again, just looking at an energy distance curve, expect to see a plot like this many times over. That's why I show it so many times. Van der Waals, very weak. Ion pairs, much stronger, okay? Much stronger, but still we're not talking about an actual bond between two things. Remember, we were in the hundreds of kilojoules per mole then. Okay, here we're down at like 20. Okay. But same basic shape. Okay. So again, ion pair equals salt bridge does not equal ionic bond. It is a type of non-covalent interaction. Okay? So the atoms are groups. How come they can be charged? So when we're talking about physiological conditions, and like I said, we're generally going to be talking about pH 7.4, 310 K, 1 atmosphere. Our solvent is always water. In the body, there's water everywhere. It just so happens, for example, glutamate, it could have a hydrogen attached to this oxygen here. Okay, this is the glutamate amino acid monomer or subunit. It happens to be more energetically favorable for the hydrogen to be off. This is a more stable structure for glutamate. Okay? And so we do have some amino acids that always are negatively charged, always positively charged. We have some that are, most actually have no charge on them. Okay? And we'll look at all of the amino acids next week. But again, here I think I just added this in PowerPoint. Here's the little dashes, so they're having an interaction. Okay? Any questions on ion pairs or salt bridges? Okay. So another type of non-covalent interaction that we're going to talk about, probably the one we're going to talk about the most going forward through the rest of the semester, will be hydrogen bonding. Okay? Covalent bonds between atoms of differing electronegativity. Okay? This is not to the extent of an ionic bond formed earlier. But covalent bonds, so here's the actual covalent bond. I'm not saying hydrogen bonds are covalent bonds. Here's a covalent bond between a carbon and a nitrogen. Here is a covalent bond between your nitrogen and your hydrogen, carbon and nitrogen, carbon and oxygen. Okay? So these covalent bonds are going to be polarized. Okay? They have some sort of electric dipole because the two atoms participating in the bond have different electronegativities. And so these arrows here are indicating, the nitrogen is more electronegative than the hydrogen, so there's this distribution of charge here. Same thing between oxygen and carbon. These happen to be pointing in the same direction of whatever this molecule might be. Okay. And so then in this case, when you have this sort of distribution of charge or this polarization, you can then have a hydrogen bond form between these two things. So polar groups or molecules tend to have strongly polarized covalent bonds. They will have moments like this pretty permanently. Nonpolar groups or nonpolar molecules really won't have any strong polarized covalent bonds in their backbone. Hydrogen bonds are going to form between two polarized dipoles that end up lining up favorably. This is going to be roughly parallel, plus or minus 25 degrees. And the length of this bond, there need to be about 3 angstroms apart in order to interact. Who knows what angstroms is in nanometers? Yes. Perfect. An angstrom is 0.1 nanometers if you want to think on the nanometer scale. Okay. 0.1. I don't know that this number is super important to me. Just never hyperfixate on exact numbers. I could write a whole class that I thought was qualitative, but you guys would hate it, so I won't. So here, this is important too. This is some language that will come up frequently. We have a hydrogen bond donor. Okay, the hydrogen bond donor is the atom that bears the hydrogen participating in the hydrogen bond. Here's the hydrogen bond. The donor has the hydrogen on it. The acceptor is the one interacting with the hydrogen. Okay? So the bond is between this hydrogen and this oxygen. I'm the donor. This is the acceptor. Water is net neutral, but it's a greedy bitch, the oxygen, or whatever we learned earlier. I love that. So it's always going to have a reasonably large dipole moment because the negative charge, the electrons will be concentrated towards the oxygen end, and the two hydrogens have more positive concentration on that end, okay? So water-water interactions are, of course, strongly influenced by this dipole dependency, and then this polar nature of water, okay? So the separation of charge is polar. Is also going to influence all sorts of other electrostatic and non-covalent interactions happening between other molecules. Okay, so for example, water can encircle actual ions, okay? Salt dissolving in water. We saw this figure too. So I just want to remind you, we have some covalent bonds here, all of this gray, but we have some polarity based on difference of electronegativity. So here, this molecule is participating in a hydrogen bond with some other molecule, and here, water has come in and broke those two things apart, and the water is actually making interactions. Okay, so what water can do is it can attenuate the strength of hydrogen bonds between biomolecules. And so this situation, it's going to be able to like flip back and forth between these two things. Okay, and this can have to do with temperature, random collision between molecules. But essentially, here we have some hydrogen bond forming. When water comes into play, as it will always come into play, water will compete off that hydrogen bond between these two molecules. And it will lower the overall strength of the hydrogen bond by possibly 5 to 20 times. I think this is a little confusing because it's like, okay, either the hydrogen's interacting there, the water is interacting with the hydrogen bond, or the molecule's interacting, like how can it lessen it? This is kind of an average over all the molecules, okay? So here's our trusty energy distance chart again. We have van der Waals up here, very weak. We have ion pairs, stronger. Hydrogen bonds fall in the middle. Okay. And then if we were to talk about putting some sort of salt bridge in water. If I wanted to redraw this graph, my salt bridge, my non-covalent interaction is being attenuated, it's being affected by water. It's going to have some sort of reduction in its strength by about 5 to 20 times. I won't give you this question on your exam or homework because I already did it the last 2 semesters, but I'll show you the answer and we can talk about it. So any drawing that kind of would fall here, even if you put it up above the H bond, that's fine. Same general shape, but I've reduced the energy. Remember, this is sort of a confusing thing. I've reduced the energy in terms of negative energy. It went up. It's a higher number overall. So this was a question I got. I wrote it down so I read it properly. From a student, if the most negative energy represents the strongest interaction and water weakens the interaction energy, is it making the energy value less negative, but the number is actually larger overall? The answer is yes. Yes. Water is making that interaction weaker. But on this plot here, weaker means less negative, okay? A shallower energy minimum, if you will, okay? It's a valid question, a lot of words there. They were right, the answer is yes. Okay. So again, what is this water attenuation, this H-bond competition? What does this mean? So in a vacuum, we might have this 3 angstrom interaction between 2 charges, and it could be as strong as negative 500 kilojoules per mole. Very, very strong. As soon as we put it in water, huge reduction. Okay? Where does this become relevant for us? We're never looking at 2 isolated charges. We might be looking at charged groups inside a protein. If they're buried in the protein's interior, they can form a really strong interaction. If they're at sort of the surface of the protein or the binding site of a protein, something like that, much lower interaction energy between those 2 groups. Any questions about this water competing for the H bonds with the molecule or this attenuation of strength?